change to this point, so we're going to pick up the 30-minute count on the next even minute. You copy, programmer?
Programmer copies next even.
Okay, there you heard it from the test director. We're going to pick up the count. Target launch time
30 minutes and counting.
will be 11:59 a.m. So again, this is the Wallops Range Control Center from in Virginia. We're counting down this morning for the launch of the Aspire payload on a Black Brant 9 suborbital sounding rocket. We've been working this morning some red conditions with winds and sea states in the recovery area, but at this point everything is reporting green for launch, so we have picked up the count. So here in about 29 minutes, we hope to be able to launch this. So again, we'll be launching the Aspire payload, and with me this morning to explain what in the heck it is that we're trying to test out this morning is Jeremy Hill with
TDSPM-01.
Jet Propulsion Laboratory.
Go ahead, sir.
What's our current status on RF avoidance?
Say again?
I was just wondering what our current status is with RF avoidance.
Not in RF avoidance.
Good morning, Keith. Thanks for having me.
Yeah, so let's see if you can talk a little bit about, what is Aspire? What is it that we're looking to test this morning?
So Aspire is an acronym. We love our acronyms at JPL. Stands for Advanced Supersonic Parachute Inflation Research Experiments. And the project was established to investigate the physics of supersonic inflation of disc-gap band parachutes. We call them DGB parachutes. Now, the Mars 2020 team will use the data from these tests to finalize the design for its mission. That mission is scheduled to launch in July of 2020. The data can also be used in planning the entry, descent, and landing of future Mars missions.
Okay. We did a previous Aspire launch back in October of last year, which was very successful. So what's the difference between, the last mission and this mission?
So the first test was a big success for us. The rocket and the parachute deployment system operated as designed. And as an added bonus, we also successfully inflated and collected data on the parachute. That data included some of the best imagery we've ever seen from supersonic parachute tests. Now, the goal of the second Aspire test is acquiring performance data on a disc-gap band parachute with some design differences.
And what are the differences between two parachutes?
Well, I guess the first place to start here would be the manufacturers of the two different parachutes. So the DGB that flown on the first Aspire test was built by Pioneer Aerospace Corporation, and the DGB being flown during the second test was built by Airborne Systems North America. Now, the first parachute was almost an exact copy of the parachute that successfully carried the Mars Science Laboratory to the surface of Mars in 2012. And while the first and second have they have similar dimensions and geometric characteristics, the parachute we're flying on the second test employs different materials and different manufacturing techniques that help make it stronger in certain key areas. We on the team have started calling it the strengthened parachute, and it incorporates stronger suspension lines, stronger materials in the canopy, about 3 times stronger than what was flown on the previous test, and only about 50% heavier.
Okay, cool. So we're getting ready for this launch, and again, as you mentioned, it is a little bit heavier payload, or parachute, and with that, of course, we have a fairly heavy payload that we're flying today at 2,700 pounds, and so that's one of the reasons why we needed a good sea state to be able to recover this. We have one of our local fishermen actually has a boat. He goes out with some of the crew from JPL, and they will go out and collect the payload once it lands and the parachute, and pull everything on board, and then bring it back to the harbor in Chincoteague, Virginia, and we'll go out with a truck later this afternoon and recover that and bring everything back here to Wallops. So right now, everything is looking good for a launch. So with this launch today, we'll be flying the Black Brant. It's a two-stage vehicle. The first stage Terrier motor burns for 5.2 seconds. It will then burn out. The second stage Brant motor then ignites at 8 seconds after launch. At this point, it's only 0.86 miles altitude. The Brant motor then burns out at 35.5 seconds at 10 miles altitude. We're expecting to reach apogee today at approximately 118 seconds into flight. At this point, it will be 31 miles altitude. This is a parabolic trajectory, and so then we'll start descent and start the parachute test after that point. And we'll call that out and let you know what's going on and how things are going with that test. So we'll begin terminal count at the T-minus 12-minute mark, and at that point you'll hear a final poll or a poll conducted to make sure that everybody is ready to begin the final countdown and for launch of the Black Brant 9 with the Aspire payload. Again, target launch time is 11:59 a.m. Okay, as you may have heard that they're going to commence with the peanuts. So Jeremy is going to describe what the peanuts are all about.
So Good Luck Peanuts made their first appearance at the Jet Propulsion Laboratory's Space Flight Operations Facility in 1964 during the Ranger 7 mission. JPL had 6 failures prior to this effort, so the pressure was on to succeed. The Ranger 7 launch day arrived, and with it came the Peanuts. One of the engineers on the project thought it might help lower anxiety, take the edge off. Ranger 7 performed flawlessly, and the Peanuts have showed up on informal countdown checklists for almost every launch since then.
Okay, so we have the Peanuts. They're being distributed in the control center, so we're getting serious and ready for launch here. Again, launch time is targeted for 11:59. We'll start the terminal countdown point at T-minus 12 minutes coming up here shortly. All right, Jeremy, while we got some time here, we're waiting for the terminal count to begin. If you can kind of explain, what the mission cost, that's always in everybody's mind for these types of projects, and kind of what's to come with the Aspire program after this mission.
So good question. Aspire is a 2-year effort, and its budget is roughly $25 million. The activity was initiated under the Mars program to help develop the test infrastructure, and the tests specifically associated with the Mars 2020 parachutes are funded by the Mars 2020 project. Now, the first flight we had, that was a shakeout test of the architecture. The second test today is to characterize the performance of our parachute. Currently, we have one more test planned for the summertime, with the possibility of at least one more flight after that.
Okay, that sounds good. So all those flights will be here out of Wallops. So right now, the earliest would be for the next flight is late summer, July at the earliest, and then we'll go from there and see how things progress. But it's been, great work with you guys, with the JPL folks on this mission, and getting ready for the Mars 2020 mission.
TD, this PM on 1.
Go ahead, sir.
We have a potential hold point at T-minus 12. Shall we forego? It's a JPL question as well.
We're not going to hold unless someone says so.
You guys want to forego step 180? Copy that. Check 180.
RSO TD, can I check item 179?
Roger. Hazard areas are clear.
Copy.
And we're just under 1 minute to pick up at the terminal count.
TD, this PM on 1. Are we ready to initiate terminal?
Permission granted. Check 181.
All stations stand by for station checks. Please announce status as green or red on channel 1 for terminal count. RC,
RC green.
MNO,
MNO green.
programmer,
Programmer's green.
LPM,
LPM is green.
PLC,
Green.
ACS, ACS green, PTM,
PTM green.
Turn,
Turn is green.
MM,
MM green.
SC,
SC is green.
SRPO,
SRPO green.
PM,
PM's green.
Arrow,
Arrow is green.
Experiment,
Experiment is green.
PI,
PI is green.
JPL,
JPL is green.
RSO, RSO is green. TD.
TD screen. All stations are responsible for reviewing the go, no-go criteria. Only stations annotated with an asterisk in the previous step are permitted to call a hold. All other sites should report red. Check 183.
RSO, ROA. RSO. Provide launcher initial wind waiting settings. Roger, stand by 1. Stand by. And ROA, this is RSO. Go ahead. Ready for settings. Settings are actuals azimuth 103.6, elevation 78.6. Copy. LCROA.
This LC.
Set launcher to wind waiting settings azimuth 103.6, elevation 78.6.
Copy and work.
10 minutes counting.
And sun rockets are unguided rockets, therefore we have to account for the winds. It's like shooting an arrow at a target. We want to shoot at a target in space. And so
PLC check
187.
final winds,
I'm going to set ground station levels and confirm. Start data recorder strip charts.
final settings are based on those winds.
ROA, this LC.
Go ahead.
Launcher settings are azimuth 103.6, 78.6.
Copy. Check 184, 185.
PM, this is MNO. Check steps 188, 189. Ground levels confirmed. Data recorders and strip charts on.
Payload is on external power.
TD, RSO on channel 1.
Go ahead, ma'am.
Roger. Just want to report that we did have a fast-moving boat come out of the inlet, but we have intercepted and confirmed he is holding.
Copy, thanks.
Still green.
This is MM.
ACS, check 190.
I'm going to record signal strength deviation for TM1. Verify nominal. M&O, you copy?
PM, this is M&O, step 191, links recorded and confirmed nominal.
Thank you, sir.
PTM, check 192, payload pressure at 15.7 psia.
ACS, check 193.
PTM, check 194.
RC, interrogate transponder, verify good code.
RC copies in work.
TD, this is RSO. We are currently red.
Hold.
7 minutes and holding.
Status.
Roger, we're currently red for ballistic wind variability. I can give you more elaboration on Channel 5.
Copy, let's go to 5.
Hey, ma'am, this is SRPO and 1. Yeah, just give us a heads up if you do get concerned, if this takes a while and you get concerned with temperatures or batteries. Copy. Thank you, sir.
Okay, again, we're at T-minus 7 minutes and holding. We're looking at the wind variabilities, and so we need to fly another weather balloon, and that should only take about 10 minutes or so to look at that and see if we're back in limits and can continue to count. So again, T-minus 7 minutes and holding for the
PM,
launch.
this is
Fire payload.
M&O on Channel 1.
Go ahead.
Copy, since we're just going to remain at T-minus 7, sounds like we're going to remain on external power. Do you want us to keep interrogating the beacons, keep strip shots on?
That's correct.
Copy that.
And PM, this is RC on 1. Transponder's good.
Check 195.
PLC, this is PTM.
Go ahead.
We are requesting to bring down Experiment 1 bus.
Copy that. Experiment 1 bus is now off.
CDR Zone 1. TDRSO, Channel 1.
Go ahead.
Roger, just give me an update. The balloon was just released before we get the data back.
Say again, you broke up. How long?
About 10 minutes.
Copy. Testing, testing, 1, 2, 3. Testing, testing, 1, 2, 3.
TD, you're good.
And we continue to hold it at T-minus 7-minute mark as the weather balloon, wind-waiting balloon has been launched, and so in about 5, 7 minutes or so, they'll start getting data and be able to crunch the numbers again. Sounding rockets are solid fuel unguided rockets, so it's like shooting an arrow at a target, and you need to account for the winds when you're shooting the arrow, and so it is with sound rockets. We need to make sure we understand exactly what the winds are and what they're doing. So that's why we're at hold at this point to fly another wind-waiting balloon and make sure that the winds are consistent from the previous.
PTM, PI on 1.
PTM.
I just wanted to check, are we recording GPS on the GUI?
That's affirmative.
Thank you.
For the launch, if you're watching on Ustream, just remember that there is a little bit of a delay from what you're seeing in the actual events. So if you're looking to go out and catch the launch, take that into account, and probably at the the T-minus 60 seconds point, you probably need to be heading outside. The launch should be visible in the Wallops region, so in the southern eastern shore of Maryland. You should be able to see it possibly up into southern Delaware. And then in Virginia, down the eastern shore of Virginia, you should be able to see it.
MM, SRPO on 1.
Go ahead.
Can you give me a call at 2515?
Copy. Okay, while we're waiting here for the wind waiting data to come in and do the analysis for setting the launcher settings, Jeremy, can you kind of tell us, what's different with this parachute from, say, a skydiver's parachute? What are we looking for?
So that's a good question. Our parachute is specifically tailored for supersonic flight in the Martian atmosphere. And the two things that you're going to notice as big differences are, first, the size of our parachute compared to a typical skydiver's parachute, and the time that it takes for the parachute to inflate. So our parachute is about 20 times bigger than a typical skydiving parachute, and it needs to be that big because of the low-density Martian atmosphere that we're operating in. Now, it might be counterintuitive, but our enormous parachutes also inflate, a lot faster than these smaller parachutes. A general skydiver's parachute.
RSO, channel 1.
Go ahead, ma'am.
Roger. The balloon data came back, and we're green as far as ballistic wind variability, but we're taking a look at the tower data. The tower data is variable. We do have some tight restrictions on the variability in the last 2 minutes of launch. So before we're comfortable picking up the count, we want to make sure that the settings are actually going to hold, and we're not going to give you a red call later on closer to 2 minutes. So we're going to need a few more minutes to take a look at it.
Copy.
Yeah, so a skydiver's parachute might inflate on the order of several seconds. The Aspire parachute will inflate in about half a second. So you've got this parachute that is 20 times bigger and inflates 10 times faster than a skydiver's parachute. So we're really talking, two different animals here. And one more little piece of visual to help with, understanding the size of these parachutes is I like to think of them in terms of like the length of a school bus. So the length of this parachute when it's fully inflated is the length of 3 school buses parked end to end. And when it's fully inflated, it's about as wide as a school bus is long. So you've got a parachute that's 1 school bus wide by more than 3 school buses long, and that's just much, much different than what you're going to see from a skydiver's parachute.
Okay, so thanks, Jeremy. That's good to be able to visualize a little bit about this parachute. And if you kind of do a search on the NASA website, there is video from the last parachute test. And just Google Aspire or whatever, and you'll be able to find that the video which was pretty cool from the last shoot. So hopefully in about a month or so we'll be able to see what this one does.
CDR, so?
Hey, ma'am.
Roger, safety's green at this time. We're ready to pick up the count.
Copy. Hey, ma'am, I'll pick it up on your call.
Yeah, let's do it at the bottom of the minute.
KLC, this is PTM.
Go ahead.
Let's go ahead and have experiment 1 bus on.
Programmer,
Copy
Yes,
that.
programmer.
Experiment 1 bus
on
is
the
up.
next even minute, please.
Roger, next, Stephen. So they'll be picking up the count here at 12:12 p.m. Eastern Time. We have 7 minutes remaining in the count, which would give us a launch time of 12:19 p.m. Eastern Time.
Seven minutes and counting.
ACS check 197 and 198.
PTM check 196.
PLC check 199200.
PTM check 201.
PLC check 202.
Experiment check 203.
And what you're hearing there during the various checks, there are various steps in the countdown, and we're currently through step 203 in the countdown. So instead of having to read out what that step is, they just yell out what step they've
PLC check 204.
Experiment check 206.
PLC check 207. Check 208.
Experiment check 209er.
PM, this is MNO, check 210, links recorded, confirm nominal.
Copy that, thank you.
ACS check 211.
RSO, ROA.
RSO.
Provide final wind weighting settings.
Copy. Settings are azimuth 102.0, elevation 79.2.
Copy. LC, ROA.
This LC.
Set launcher to final wind weighting settings of azimuth 102.0, elevation 79.2.
PLC check 212.
ROA, this is LC.
Go ahead.
Settings are at azimuth 102.0, elevation 79.2.
Copy. Check 213-214.
Arrow check 216.
PLC check 215.
ACS check 217.
PLC check 221.
RC interrogate transponder, verify good signal on internal.
RC reports no change on internal.
Verify no change in signal strength deviation for all.
And the payload.
Experiment check 222.
PM, this is M&O, check 220, no change.
ACS check 218.
Two minutes.
PLC check 225.
Check 223.
PM, this is RC, you can check 219, no change in internal power.
Turn check 224.
PLC checks 228, 229, 230, 231.
ACS check 226, 227.
PTM check 232, 233.
PLC go.
Go.
PTM.
PTM go.
ACS.
Go.
Turn. Turn go. JPL.
1
JPL
minute.
go. MM's go. Check 235.
Vehicle and payload are go for launch.
50 seconds. Minus 40.
Booster armed.
Minus 30. Minus 20.
ACS check 236.
Minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, mark.
We have first stage burnout. Second stage ingestion. Second stage burnout. At this point, the vehicle is flying at 3.2 Mach. payload has despun.
We've received telemetry indicating that the DGB parachute has deployed and inflated. The Aspire team will now be marshaling recovery boats to converge on an anticipated splashdown point so that they can retrieve the parachute and the valuable data carried aboard the vehicle. As a reminder, the data about the deployment of the payload and data about parachute inflation is on board.
Okay, as it looks, we had a good launch this morning of the Black Bear 9 carrying the Aspire payload. We did have good chute deployment, and the payload with their chute is now descending. We'll land in the Atlantic Ocean where we'll have the recovery team pick it up and bring it back this afternoon to the docks at Chincoteague, Virginia, and then we'll go out and pick that up and bring it back here to Wallops where they can pull off the data tapes and the video information and start to analyze and see how the parachute performed today. So our next Aspire launch is currently slated for no earlier than July, and so we will look forward to that mission. The next mission from here at Wallops, currently on schedule, is Orbital ATK's Antares rocket carrying supplies to the International Space Station. That will occur, right now we're looking at sometime in mid to late May. And then in June, late June, we also have the Rock on Rocksat C-Student program launch, and which we do annually. This, I think, coming up on the 11th or 12th year, and so we look forward to that. So from the Wallops Range Control Center, that pretty much concludes. Jeremy, do you have anything to add on to this?
I just want to say thank you for having me. It's been a pleasure.
Well, it's been good having your insight into the mission, since I'm not an engineer, and understanding everything that goes on with these tests. And so, again, we look forward to the next test. And so this is Wallops Range Control signing off.